Hello everyone, it's me Krishna Rai, bearing roll number 21NS0167, Physics Honours from Namche Government College, South Sikkim. And I am here to talk on the topic XRF technique. So, first we have introduction. X-ray fluorescence, XRF spectrometry is an elemental analysis technique with broad application in science and industry. XRF is routinely used for the simultaneous determination of elemental composition and film thickness. Modern XRF instruments are capable of analyzing solid, liquid, and thin film samples for both measure and trace ppm level components. The analysis is rapid and usually sample preparation is minimal or not required at all. Next, history of XRF. The history of XRF dates back all the way to 1895 when German physicist Wilhelm Conrad Roentgen accidentally discovered X-rays while studying cathode rays in high voltage gaseous discharge tube. However, the possible use of X-rays for analysis went unnoticed until 1913, when Henry Moseley established the specific relationship between the wavelength of a characteristic X-ray photon and the atomic number of the excited element. In 1925, X-rays were used for the first time to excite a sample, but the technique was only made practical in 1940 and the first commercial XRF spectrometers were produced in 1950. Next, fundamental principle of XRF. Now let us learn its principle. Number 1. XRF works on methods involving interaction between electron beams and X-rays with samples. Number 2. Made possible by the behavior of atoms when they interact with radiation. Number 3. When materials are excited with high energy, short wavelength radiation, example X-rays, they can become ionized. Number 4. If the energy of the radiation is sufficient to dislodge or tightly held inner electron, the atom becomes unstable and an outer electron replaces the missing inner electron. Number 5. When this happens, energy is released due to the decreased binding energy of the inner electron orbital compared with an outer one. Next we have is application. Application of XRF. It is a method of elemental, metal and non-metal analysis with atomic number greater than 12. Quantitative analysis can be carried out by measuring the intensity of fluorescence at the wavelength characteristic of the element being determined, especially applicable to most of the elements in the periodic table. XRF is also applicable in terms of medicine, like direct determination of sulfur in protein. The sulfur content of each of the many different forms in which protein exists in human blood varies considerably. XRF indicates protein distribution and provides a diagnostic link for the medical practitioner. Determination of chloride in blood serum. Determination of strontium in blood serum and bone tissue. Elemental analysis of tissues, bones and body fluids. It is used for determination of trace elements in plants and foods. It is also used for detection of pesticides on fruits and herbal drugs. Advantage of XRF. XRF is a versatile, rapid technique. It is non-destructive method of chemical analysis, important as in case of samples in limited amounts or valuable or irreplaceable. It is precise and with skilled operation it is accurate. Applicable to a wide variety of samples from powders to liquids. It is convenient and economical to use, with the major input cost being the hardware itself, which averages around $75 for a modern industrial use spectrometer or $12,05,000 for a research quality instrument. The instruments have few moving parts, tend to be low maintenance, and on a regular basis consume only liquid nitrogen and electricity. Next, disadvantage of XRF. Disadvantages include fairly high limits of detection (LODs) when compared to other methods. Possibility of matrix effect, although this can usually be accounted for using software-based correction procedures. LODs are graphite furnace atomic absorption spectroscopy (GFAAS) beat XRF by several orders of magnitude, but analysis can exhibit substantial matrix effects. GFAAS is also relatively slow, with one element determined at a time, and is destructive. PXRF instruments are capable of producing results comparable in many ways to the lab-based XRF at a fraction of the cost. PXRF instruments can be purchased for about $30 to $50, complete with vacuum system, sample changer, and accompanying computer. Now, XRF. How does it work? An XRF spectrometer works because if a sample is illuminated by an intense X-ray beam known as the incident beam, some of the energy is scattered, but some is also absorbed within the sample in a manner that depends on its chemistry. The incident X-ray beam is typically produced from a RS target, although W, MO, CR, and others can also be used depending on the application. When X-ray hits sample, the sample emits X-ray along a spectrum of wavelength characteristic of the type of atoms present. If a sample has many elements present, the use of a wavelength dispersive spectrometer allows the separation of a complex emitted X-ray spectrum into characteristic wavelength for each element present. Various types of detectors used to measure intensity of emitted radiation. Examples of detectors used include the flow counter and the scintillation detector. Flow counters measure long wavelength less than 0.15 nm X-rays typical of elements lighter than zinc. The scintillation detector is commonly used to analyze shorter wavelength in the X-ray spectrum, T spectra of element from Nb to 1, L spectra of TH and U. Now, the instrumentation. Two different types of measurement system are used in XRF. Number 1, wavelength dispersive X-ray fluorescence. Number 2, energy dispersive X-ray fluorescence. WDXRF. In WDXRF, the emitted X-rays are dispersed based on their wavelength. Number 2, gas ionization and scintillation detectors are found in this system. Number 3, high resolution is produced. EDXRF. The energy dispersive system collects all X-ray photons simultaneously onto the detector. Each photon generates an electrical pulse with an amplitude proportional to energy of X-ray photon. Solid-state semiconductor detectors are found in this system. Limitation. In theory, the XRF has the ability to detect X-ray emission from virtually all elements depending on the wavelength and intensity of incident X-rays. However, in practice, most commercially available instruments are very limited in their ability to precisely and accurately measure the abundance of the elements with Z less than 11 in most natural earth materials. XRF analysis cannot distinguish variation among isotopes of an element, so these analyses are routinely done with other instruments. XRF analysis cannot distinguish iron of the same element in different valence states, so these analyses of rocks and minerals are done with techniques such as wet chemical analysis or Moser spectroscopy. Now, conclusion. The XRF method of characterization provides a vast and reliable way of acquiring information on the elementary composition and chemical state. Thank you.